Beneath the streets of downtown Seattle, beneath the skyscrapers, the coffee shops, the waterfront piers where tourists photograph the Olympic Mountains, there's a network of fractures in the Earth's crust that scientists thought they understood. They had mapped the big fault. They had calculated how often it moves. They plugged those numbers into the National Hazard Model and told a metropolitan area of 4 million people that the worst-case scenario, the big one, probably wouldn't happen for thousands of years. Then, in January 2026, researchers published a study that changed the math entirely. What they found wasn't a new fault, but something more unsettling. The smaller faults already sitting beneath the city, the ones almost nobody was paying attention to, had been rupturing far more often than anyone realized. Not every few thousand years, roughly every 350 years. And the last time one of them moved was possibly just 2 centuries ago. That timeline doesn't leave much of a buffer. So why did this contradiction exist in the first place? Why did the National Hazard Model leave these faults out of its calculations? And what does it mean for the millions of people living on top of them right now, going about their ordinary days, entirely unaware of what the ground beneath them has been quietly doing? Let's get into what scientists just found beneath Seattle and why it caught them off guard. Seattle, Washington, has a population just over 700,000 in the city proper, but stretch the map to include the broader Puget Sound metropolitan area, and you're looking at more than 4 million people. It's the largest city in the Pacific Northwest, the economic engine of Washington state, and home to some of the most valuable real estate on the West Coast. The Space Needle rises above the skyline. Container ships pass through the Port of Seattle, one of the busiest trade hubs in North America. Tech campuses sprawl across Bellevue and Redmond, and all of it sits on ground that has been shaking, cracking, and rearranging itself for millennia. Most people who live in the region know about the earthquake risk in general terms. The general understanding is that the Cascadia subduction zone, a massive fault system offshore, running from Northern California to British Columbia, is the one to worry about. And that's true. Cascadia is capable of producing a magnitude 9.0 earthquake, the kind that shakes for 3 to 6 straight minutes and sends tsunami waves crashing into the coast. The last time it ruptured was January 26, 1700. That earthquake W, as so powerful that the resulting tsunami crossed the Pacific Ocean and struck the shores of Japan, where it was recorded in historical documents. Nearly 300 years later, scientists used those Japanese records to calculate the exact timing of the Cascadia event, working backward from the speed of the tsunami waves. That puts the last rupture 326 years in the past. The average recurrence interval for Cascadia earthquakes falls somewhere between 300 and 600 years, which means the next one could happen tomorrow, or well over a century from now. That uncertainty is part of what makes it so difficult to plan for. But Cascadia isn't the only seismic threat in the region, and the study that shook the scientific community in 2026 focused on a danger much closer to home, literally beneath people's feet. The Seattle Fault Zone is an east to west trending fault system stretching roughly 75 kilometers, about 46 miles, from the foothills of the Cascade Range east of the city all the way to Hood Canal on the Olympic Peninsula to the west. It cuts directly through downtown Seattle, beneath the waterfront, beneath the stadiums where the Seahawks and Mariners play, beneath the historic brick buildings of Pioneer Square. This isn't some distant offshore threat. This is a fault system running directly under one of America's largest cities. Geologists started seriously studying the Seattle Fault Zone in the early 1990s. They were intrigued by odd gravitational readings, by stair-step geological formations along the coastline called marine terraces, and by growing evidence of an ancient tsunami that had swept through Puget Sound roughly 1,000 years earlier. As they dug deeper, sometimes literally, the picture that emerged was alarming. In approximately 923 CE, a magnitude 7.5 earthquake ruptured the main Seattle Fault. The ground heaved. Shorelines along Puget Sound were thrust upward by as much as 8 meters, roughly 26 feet, almost instantaneously. Coastal areas around what is now Restoration Point were violently uplifted. Submarine landslides were triggered, and locally generated tsunamis swept across the inland waterways. The evidence is written into the geological record multiple ways: sediment layers with sandy tsunami deposits, and drowned forests of ancient Douglas fir trees, trunks preserved at the bottoms of lakes, telling the story of landscapes flooded or buried by earthquake-triggered landslides. In 2023, researchers led by Brian Black at the University of Arizona used dendrochronology, or tree ring analysis, to pin down the timing with extraordinary precision. Cross-matching ring patterns against a 1,300-year reference chronology, they narrowed the date to a 6-month window between the fall of 923 CE and the spring of 924 CE. The findings got even more unsettling from there. The tree ring data showed that the Saddle Mountain Fault, a separate system slicing across the Olympic Peninsula near Lake Cushman, matured at the same time. Divers had used hydraulic chainsaws to retrieve wood samples from drowned forests at the bottoms of lakes, and the ring patterns from trees killed at Saddle Mountain matched the same death window as trees killed along the Seattle Fault. Two faults, separated by miles, had either ruptured simultaneously in a single composite earthquake of roughly magnitude 7.8, or in two closely spaced events of magnitude 7.5 and 7.3. Either scenario is unsettling for modern Seattle, since current hazard models don't fully account for multi-fault ruptures of this kind. A magnitude 7.8 Earth QO, AK directly beneath a modern city, would release roughly 38 times more energy than a magnitude 6.7 event, trigger a local tsunami, and cause catastrophic damage to infrastructure built for much smaller quakes. The 923 event appears to have been the most intense seismic episode in Puget Sound since the end of the last ice age, roughly 16,000 years ago. But here's where the story takes a turn. For years, scientists focused their attention on the main Seattle Fault, the big one at the core of the fault zone. They knew it produced the 923 earthquake. They estimated its recurrence interval at greater than 5,000 years, meaning it probably wouldn't rupture again for a very long time. From a pure probability standpoint, that was somewhat reassuring. The problem is that the Seattle Fault Zone isn't just one fault. It's a network, a complicated mesh of primary and secondary fractures that together absorb the compressive stress B yielding up in the Earth's crust between Portland, Oregon, and Vancouver, British Columbia. The main fault gets the attention because it produces the biggest earthquakes, but the secondary faults have their own seismic histories, and until recently, almost nobody was studying them closely. Dr. Stephen Angster is a research geologist at the USGS Earthquake Science Center in Seattle. His specialty is paleoseismology, figuring out when and how often faults rupture by reading the geological evidence left behind by ancient earthquakes. Think of it as forensic geology, working a crime scene thousands of years old, piecing together clues from soil layers, rock formations, magnetic anomalies, and buried surfaces to reconstruct what happened and when. Angster's focus for the study, published in January 2026, was two specific secondary faults, the Little Beach Fault and the Vasa Park Fault. These are shallow, south-dipping structures sitting within the hanging wall of the greater fault system, on trend with the primary blind Blakely Harbor Fault, sharing a similar orientation and mechanical relationship, but shorter, much shorter, and zone we don't fully understand how these secondary faults interact with the main fault and with each other. Harold Tobin, a geophysicist at the University of Washington and head of the Pacific Northwest Seismic Network, wasn't involved in either of the 2026 studies but reviewed the findings. His assessment: the giant 923-style earthquake, the one that uplifted shorelines by 26 feet and sent a tsunami through Puget Sound, appears to have been the only event of its magnitude in 11,000 years. That's the good news. The recurrence interval for the absolute worst-case scenario on the main fault appears to be very long, but the less bad, still bad scenarios, as Tobin described them, are more likely than anyone previously thought. A magnitude 6.5 to 7.0 earthquake on a shallow secondary fault directly beneath Seattle would cause billions of dollars in damage, potentially kill hundreds or thousands of people, and severely disrupt the region's economy and infrastructure for months or years. And the probability of that scenario just went up based on the new data. It's worth stepping back to understand the tectonic forces creating all of this. The Pacific Northwest sits at a convergent plate boundary, where the Juan de Fuca plate, a remnant of the much larger Farallon plate, is slowly diving beneath the North American plate. This process, S-subduction, happens at roughly 40 millimeters per year. As the oceanic plate slides under the continental plate, it drags and compresses the crust above, building stress in the rock until that stress exceeds the rock's strength and it breaks. That break is an earthquake. The Cascadia subduction zone is where the Juan de Fuca plate locks against the North American plate along the coast. The shallow crustal faults inland, including the Seattle Fault Zone, the Tacoma Fault, the Olympia Fault, and the Saddle Mountain Fault, are a secondary consequence of this same subduction process, driven by the same north-south compression combined with the clockwise rotation of the overlying plate. As many as 13 active shallow fault zones have been identified between roughly the 47th parallel and the U.S.-Canadian border, together producing dozens of moderate to large earthquakes over the past 16,000 years. But none of these faults have ruptured during the historical period, the era of written records and seismic instrumentation, which only goes back to the mid-1800s. Everything we know about their behavior comes from paleoseismology, from reading the clues left behind in rocks, soil, and buried forests. That's what makes Angster's study so significant. Every new earthquake added to the paleoseismic record changes the probability calculations. Every new date narrows the uncertainty windows. And the picture emerging from the data is more complex and more concerning than the simple model suggested. Elizabeth Davis, an earthquake geologist at the University of Washington who led a companion study published in the journal Geology, approached the question from the opposite direction. Instead of studying the secondary faults, Davis focused on the main fault and tried to extend the record of its largest earthquakes further back in time. Her team mapped more than 150 marine terraces around Puget Sound, measuring their depths and estimating how much uplift had occurred over the past 11,000 years. Looking for evidence of 923 scale events, they didn't find any. The 923 CE earthquake was the only event of that magnitude in the entire 11,000-year record. That suggests the recurrence interval for the absolute biggest earthquakes on the Seattle Fault is very long, possibly longer than 10,000 years. But Davis was careful to qualify the finding. Thick sediment layers could potentially mask smaller events. And smaller, in this context, is relative. A magnitude 6.5 earthquake directly beneath a major city is not a minor event. It simply wouldn't produce the same dramatic uplift signals her survey was designed to detect. What the two studies together paint is a portrait of a fault system that's more nuanced and more dangerous in its complexity than the simplified models captured. The big event is rare, but the medium-sized events, the ones that can still kill people and destroy infrastructure, happen much more often than scientists had calculated, and the tools the government uses to assess risk weren't designed to account for them. The irony is that Seattle has invested enormous money and effort in earthquake preparedness over the past 2 decades. The city replaced the seismically vulnerable Alaskan Way viaduct with a modern tunnel. Building codes have been updated. The Shake Alert early warning system, run by the USGS with state agencies, can now provide 10 to 90 seconds of warning before strong shaking arrives, enough time to drop under a desk or stop a train. Evacuation routes for tsunami inundation zones have been designated and emergency supplies stockpiled. But much of that planning was Cali, braided to the known threats. The Cascadia megathrust offshore, and the rare but massive rupture of the main Seattle Fault. The secondary faults, with their shorter recurrence intervals and capacity to produce damaging earthquakes right beneath the urban core, represent a gap in the preparedness framework, a gap Angster's study has now made impossible to ignore. The Washington State Department of Natural Resources estimates an 85% chance of at least a magnitude 6.5 deep earthquake in the Puget Sound region within the next 50 years, a 15% chance of a magnitude 9 Cascadia megathrust event in that same time frame, and a 17 PE arson chance of a magnitude 6.5 or greater shallow crustal earthquake near the urban core. That last number is the one the 2026 study could potentially revise upward. If secondary faults rupture every 350 years, the last known event was around 200 years ago, and these faults can produce earthquakes up to magnitude 6.7, then the probability of a shallow crustal earthquake beneath Seattle in the coming decades may be higher than current models suggest. Whether these secondary faults get incorporated into the next update of the National Seismic Hazard Model remains an open question. Angster has expressed hope that further research will justify their inclusion, but updating the model involves years of scientific review, peer evaluation, and policy discussion. Meanwhile, the faults don't wait for committees. The earth beneath Seattle is under constant compression. Stress is accumulating along every fault in the system, from the locked Cascadia megathrust offshore to the shallow crustal faults beneath the suburbs in the city center. That stress will be released. The only questions are where, when, and how violently. For the 4 million people living in the Puget Sound metropolitan area, the message from the 2026 study isn't that they need to panic. Panic doesn't save anyone. The message is that the threat profile is more complex than the public has generally been told. The danger isn't just the monster earthquake on the big fault, it's the moderate earthquake on the small fault nobody was watching. The one that ruptures a few kilometers beneath office buildings and apartment towers and century-old brick warehouses, without the narrative buildup of the big one, without decades of media coverage, the one that could happen on an ordinary afternoon and reshape a city before anyone has time to understand what's going on. A 2005 scenario model for a magnitude 6.7 earthquake on the Seattle Fault estimated at least 1,600 deaths and $50 billion in damage. That model was built before scientists knew the secondary faults were this active, before they found evidence of a rupture event as recent as the early 19th century. The numbers, if recalculated with the new data, would likely look different, possibly much different. The Earth beneath Seattle did something scientists didn't expect. It showed them that the faults they'd been ignoring are more active, more frequent, and more dangerous than the hazard models assumed. And while that revelation doesn't change the ground beneath anyone's feet, it should change the conversation about what that ground might do next. As of today, The secondary faults in the Seattle fault zone remain excluded from the National Seismic Hazard Model. Dr. Angster and his team continue their research. The retrofit program for Seattle's unreinforced masonry buildings continues to lag behind schedule, and stress continues to build silently and invisibly along every fault in the system. The clock is running. It always has. The difference now is scientists have a better idea of what it's counting down to. And the interval, per the newest data, is shorter than anyone assumed. Tuesday brings another significant round. A threat for severe storms and heavy rain returns to the Midwest, extending into the Great Lakes and Mid-Atlantic. Damaging winds should be the primary concern on Tuesday, but the atmosphere stays explosive through the day. When daytime heating pumps energy into an already unstable atmosphere and a line of thunderstorms rolls through, those storms can intensify fast. A wind gust that starts around 50 miles per hour can spike to 80 or 85 miles per hour within minutes during a storm's most intense phase. Forecast models point to widespread rainfall totals of 1 to 2 inches across Wisconsin, Illinois, Michigan, and Indiana, with localized amounts exceeding 2 to 3 inches. That kind of rainfall on already saturated soil isn't a minor inconvenience, it's a genuinely life-threatening flash flood situ. P. The National Weather Service issues flash flood emergencies, its highest level of alert, for exactly these conditions. In event after event across this country, some drivers try to push through flooded roads and don't make it. Do not be that driver this week. If you see a flooded road, turn around. The water is almost always deeper and moving faster than it looks. Wednesday continues the same pattern. A moist axis is forecast to stay in place from the Central Plains east-southeastward into the lower Ohio Valley, keeping the severe weather threat alive through midweek. The same areas hit Monday and Tuesday face another round Wednesday. 3 consecutive days of severe weather in the same regions. That kind of repetition matters more than people think, because the damage isn't just about any single storm, it's the compounding effect. Power restoration crews working through Monday's outages get interrupted by Tuesday's storms. Wednesday brings a third wave on top of that. Emergency crews get spread thin. Utility workers can't safely work during active lightning. Roads blocked by trees from Monday become barriers for emergency vehicles responding to Wednesday's flooding. It's a cascading effect, and that's exactly what parts of the Midwest are facing this week. There's another layer to this compounding problem that doesn't get talked about enough: insurance and recovery timelines. When a region gets hit by one significant storm, adjusters and repair crews can usually mobilize and start working through the damage within days. When a region gets hit by 3 or 4 significant storms in the same week, the process backs up fast. Roofing crews that would normally move from house to house get overwhelmed. Tree removal services get booked out for weeks, families whose basements flooded on. Monday may not even have had a chance to start pumping out water before Tuesday's storm adds more. This isn't just a meteorological event. It becomes a logistical one for entire communities. And recovery from a compounded week like this one tends to take far longer than recovery from a single isolated severe weather day. Now let's zoom out, because this week isn't an isolated event. It's the peak of what has already been an extraordinary severe weather year for this part of the county. RI. In Illinois alone, the preliminary tornado count for 2026 sits at 145, compared with 147 finalized for all of last year. And last year's Illinois tornado total was already the highest since 1950. Illinois is on pace to break its own record from the year before, and that year was already historic. One state, 145 tornadoes, and the year isn't over. The lower Great Lakes region has been a hotspot for severe weather all through 2026, with a corridor stretching from eastern Iowa into southern Wisconsin and northern Illinois being especially active. And this week is adding to that total in real time. It's worth looking back at July 27th, because that event shows just how loaded the atmosphere has been all summer. Heat and oppressive humidity that day created extreme instability, providing plenty of fuel for severe weather. A relatively subtle disturbance interacting with that instability produced a narrow but intense corridor of thunderstorms from eastern Wisconsin into northeastern Illinois. The National Weather Service issued multiple tornado and severe thunderstorm warnings that day. And here's the number that tells you how wild this summer has been. One of those storms produced a wind gust of 111 miles per hour in south-central South Dak. HOTA, not a tornado, a straight-line wind gust from a thunderstorm at 111 miles per hour. That's close to Category 3 hurricane strength from a summer thunderstorm. Severe storms also rolled through the Dakotas and northern Minnesota that day, producing widespread reports of damaging wind along with some hail and tornado reports. These are not normal summer thunderstorms. The atmosphere this summer has carried a level of instability we rarely see in August, and meteorologists have said so directly. The last time a pattern like this, multiple consecutive days of elevated severe weather risk across the Midwest and Ohio Valley in August, showed up was 4 or 5 years ago. This is a genuinely rare August storm pattern, and it's happening right now. It's worth pausing on why this particular combination, high instability, a stalled heat dome, and repeated rounds of storms tracking over the same corridor, is so much rarer than a single severe weather day. Most summer severe weather events are transient. A cold front sweeps through, triggers a line of storms, and then the atmosphere resets behind it as cooler, drier air moves in. What makes this pattern different is that the heat dome isn't moving. It's parked over the southern plains, essentially acting as a wall that redirects storm systems along the same track day after day instead of letting the pattern flush out. That's the mechanical reason this keeps repeating instead of resolving after a day or two, and it's also why models are struggling to pin down exactly when this breaks. As long as that dome holds its position, the setup along its edge keeps regenerating. While the Midwest is getting hammered by storms, the southern plains and southeast are baking under the same heat dome that's driving all of this. The storm pattern producing damaging winds is enfolding alongside dangerous heat and humidity under that dome. Typically, under a heat dome like this, there's very little air circulation, which means air quality alerts often follow, especially in urban areas. High heat combined with St. Agnan air lets ozone build up, and air quality can shift from moderate to unhealthy within hours. People with asthma or other respiratory conditions, elderly people, and young children are all at elevated risk on days like this, even if they're nowhere near the actual thunderstorms. The heat dome isn't just uncomfortable. For vulnerable populations, it's a genuine health emergency. Extended heat like this can lead to widespread power outages, deteriorating air quality, and rising rates of heat exhaustion, particularly for people without reliable access to air conditioning. It's also a real risk for people who spend time in cooling centers during the day and then return to unair-conditioned homes in the evening, where heat-related illness can still take hold. Most people don't realize that heat doesn't stop being dangerous at night. When overnight temperatures stay above 80 degrees Fahrenheit, the human body can't cool down properly, and heat-related illness can develop even while someone is asleep in an unair-conditioned home. In this pattern, with thunderstorms knocking out power to thousands of homes at the same time, extreme heat is building. The combination of storm damage and heat becomes genuinely dangerous. Looking further ahead, this pattern doesn't wrap up midweek. Storm activity is expected to keep pressing eastward through Thursday and Friday, while the western Midwest sees some temporary relief. That relief won't last. By late Friday into Saturday, there are signs that another round of severe weather could build across Minnesota, Iowa, and Wisconsin. Damaging winds, hail, and tornadoes all possible again. By Sunday, the trailing edge of this system pushes into the Great Lakes and Ohio Valley for yet another round. If you're counting, that's potentially 6 to 7 consecutive days of severe weather threat across this region. Not every day will be equally